at Mehra Research Institute, now Harish Chandra Research Institute at Uttar Pradesh. She currently works as an independent researcher and has several visiting faculty positions. Now I welcome Professor to introduce the speaker to us. Over to you, ma'am.
Thank you very much for giving me an opportunity for chairing the endowment lecture of Professor Sambat Kumar. And I'm very happy to do so. And this lecture will be delivered by Professor Lagrange. And just few sweet words I would like to introduce to the participants. Professor Lagrange is Associate Professor at Livingston College. He did his PhD from University of Tennessee in 2008, MS from Western HUP University, then BS from University of Southern Indiana. After degree in 2008, his title of the thesis was Zero Divisor Graphs, Commutative Rings of Quotients and Boolean Algebra. And since 2010, he is teaching at the same university, Livingston College. His specialization is in Commutative Algebra and Discrete Mathematics, and his research work is in compressed zero divisor graphs of rings and graph spectra. He has published 40 research papers in leading international journals like Algebra and Discrete Mathematics, and he is a reviewer to many leading journals. And with these lines, I request Professor Lagrange to deliver Professor E. Sambat Kumar endowment lecture. So I send the mic to you. Please continue.
I'd like to thank the organizers of this conference for kindly giving me the opportunity to speak today on divisor graphs and theorems related to Boolean algebra structure and commutative rings, where in this talk, we will consider several theorems showing certain ways in which graphs have been used to expose algebraic structure. And so for this, we'll begin by introducing the different types of graphs that will be relevant in this talk. So to begin with, all rings in this talk will be commutative, but not necessarily with an identity element. And given an element X of a ring, the X divisor graph will be denoted by a gamma sub X. And here the vertices are all of the divisors of X, and two distinct vertices R and S will be adjacent precisely when their product is equal to X. And so for example, here we have the 12 divisor graph of Z mod 18, where, for example, notice that 6 is adjacent to 2 since 6 times 2 is equal to 12. And more generally, here we have, let's see if I can zoom out. Here's the complete set of all of the X divisor graphs of Z mod 18. So for example, down here, you can see the graph that we introduced on the previous slide. And here's the zero divisor graph of this ring. And note that each of these divisor graphs has either one or two components up to isomorphism. So for example, here, although there are 3 components for this divisor graph, there's only one component up to isomorphism. And we will see later that this is always the case if R happens to be a von Neumann regular ring. But also note that Z mod 18 is not a von Neumann regular ring. And so this example suggests that perhaps there are some results out there that could still be had that are more general. The next type of graph that we'll consider is the compressed divisor graph associated with X, which we will denote by D sub X. And this E stands for equivalence because the vertices will be the equivalence classes of associates. of non-trivial divisors of X, where by non-trivial, we mean that we're not going to consider any units, and we're also not going to consider any associates of X. And then two distinct vertices will be adjacent precisely when the product of any two representatives is a divisor of X. So notice, in contrast to the first definition, where the product must equal X, in this definition, that condition is relaxed so that the product only needs to divide X. And so this definition warrants an illustration. And I'll go ahead and ask, can everybody still see my screen okay?
That's okay, fine.
Okay, good, very good. So to illustrate this definition, we're going to construct the compressed divisor graph associated with 12 in the same ring that we looked at earlier, Z mod 18. And here I've written down the same 12 divisor graph that we saw on the earlier slides, because this graph will give us the list of all of the divisors of 12. So first, let's delete these edges. And now we have all of the divisors of 12 in Z mod 18, but we do not want to consider any of the units in the ring. And the units are precisely the elements of this column. So we're going to delete those. But we also want to delete all of the associates of X. And 6 and 12 are the only associates of 12. And so we will delete those as well. And now we are left with the non-trivial divisors of 12. But we want to identify elements that are associates. And so here you can see that in this column, we have all associates of 2. And in this column, we have associates of 3. So we will identify those elements, and we're left with just 2 vertices for the compressed divisor graph. And of course, since 2 times 3 equals 6, which is a divisor of 12, there's an edge between those vertices. And so here we have the compressed divisor graph associated with 12 for this ring. The next type of graph that we'll consider is Bex graph. And this is a little bit redundant because Bex graph is just the X divisor graph with X set equal to 0. So note that for Bex graph, every element of the ring will be a vertex because every element of the ring divides 0. We'll also consider the unrestricted Bex graph, which we'll denote by gamma star. And this is the same as Bex graph, except now vertices will be allowed to be adjacent to themselves. And so here we have Bex graph for Z mod 4. And then the unrestricted Bex graph is the same graph, except now 0 is adjacent to itself and 2 is adjacent to itself as well. The fifth kind of graph that will come up in this talk is the Anderson-Livingston graph. And this is just the subgraph of Bex graph that's induced by the non-zero zero divisors of the ring. And this is probably the most well-studied out of all of the divisor graphs that we'll consider in this talk. The last type of graph that will come up in this talk is the zero divisor graph of a partially ordered set, which was introduced by Liu and Wu, at least in the context of the current definition. And in this graph, the vertices are the non-zero elements P, such that there exists a non-zero element Q, where 0 is the only lower bound of both P and Q. And here we're denoting the least element of the partially ordered set by 0. And here 2 distinct vertices are adjacent precisely when 0 is their only lower bound. And so it's worth noting an interesting link between the zero divisor graphs of partially ordered sets and the Anderson-Livingston graphs. because it will show that how zero divisor graphs of partially ordered sets can be viewed as generalizations of zero divisor graphs of rings. So to illustrate this, first consider any Boolean ring R. Note that a Boolean ring can be partially ordered by defining R less than or equal to S if and only if R times S is equal to R. And it turns out that under that partial order, the Liu-Wu graph, so the zero divisor graph where R is regarded as a partially ordered set, turns out to be equal to the Anderson-Livingston graph where R is regarded as a ring. And actually, this result can be generalized as follows. So given any element R of a ring, and here the ring does not have to be Boolean, if we consider the equivalence class of all the elements that have the same annihilator as R, and then fix any arbitrary linear order on these equivalence classes, then the ring will become partially ordered by defining R less than or equal to S, if and only if either the annihilator of S is properly contained in the annihilator of R, or if those annihilators are equal and R is already less than or equal to S in that predetermined linear order on the equivalence classes. Then under that partial order, if the ring does not have any non-zero nilpotent elements, then once more we find that the zero divisor graph of R regarded as a partially ordered set coincides with the zero divisor graph of R when regarded as a ring. And so we see that in these cases, zero divisor graphs of partially ordered sets generalize zero divisor graphs of rings. And I'll also point out that this second case is a generalization of the first case, because in the second case, if R happens to be a Boolean ring, then this definition is nothing more than the definition that was already given in the first case. Excuse me. So now that we've become acquainted with the graphs that will be relevant in this talk, we'll move on to a characterization of zero divisor graphs of Boolean rings, because zero divisor graphs of Boolean rings will have an essential role in this talk. And this characterization kind of tells us what these graphs are. So the theorem states that a ring is Boolean if and only if all the vertices of the zero divisor graph will have a unique complement. And so, for example, here we have the zero divisor graph of the Boolean ring of order 8. And if we pick a vertex, note that it's an incident with exactly one edge that's not an edge of any triangle in the graph. Any other edge that it is incident with will be an edge of a triangle in the graph. And that is what it means to have a unique complement. Zero divisor graphs of Boolean rings turn out to arise in many other contexts as well, even if it happens to be the case that the ring does not have zero divisors. So for example, here we see a ring is a unique factorization domain. So if the ring is a unique factorization domain, and if X is square free and not irreducible, then its compressed divisor graph will be isomorphic to a zero divisor graph of a Boolean ring. To illustrate, of course, you see this is the graph from the earlier slide. It's isomorphic to the zero divisor graph of the Boolean ring on 8 elements. But it's also the compressed divisor graph of any element that's a product of 3 distinct primes in a unique factorization domain. And it's easy to see why this result holds, since it can be checked that the compressed divisor graph is just the zero divisor graph of the Boolean ring of subsets of the collection of all distinct prime divisors of X. Another context in which zero divisor graphs of Boolean rings arise involves X divisor graphs, which we'll come to shortly. But first, I want to point out that the compressed divisor graphs can be used to give a characterization of unique factorization domains. So it turns out that the property that I just mentioned of compressed divisor graphs being isomorphic to Boolean rings does not give the characterization, because there do exist non-unique factorization domains such that the compressed divisor graphs are zero divisor graphs of Boolean rings. However, if we consider the property of dominance, then we can get a characterization. So recall that a clique is dominant if every vertex of the graph is either a member of the clique or adjacent to a member of the clique. And so back to the zero divisor graph of the Boolean ring on 8 elements, we see that this triangle is a dominant clique. And that turns out to give us our characterization. So an integral domain will be a unique factorization domain if and only if all of its compressed divisor graphs are finite with a dominant clique or the null graph. So for example, if X happens to be irreducible, then the compressed divisor graph will be null. But in all the other cases, it will be finite with a dominant clique. Moving on to, as I mentioned before, seeing zero divisor graphs of Boolean rings in the context of X divisor graphs, it turns out that X divisor graphs of Boolean rings will always be isomorphic to zero divisor graphs of Boolean rings. To illustrate that property, here I've written down the zero divisor graph of the Boolean ring on 16 elements. And we're going to pick an element X from that ring. So let us choose the element that has a 1 in the first component and zeros in all of the other components. Then it's easy to check that the divisors of that element consist of all of the elements that have a 1 in the first component. And that's easy to check because clearly multiplying any of these elements by X will result in X. And so these are the divisors of X. And I've distinguished these two elements here because they are the trivial divisors. Of course, this is X, and this here is the identity element. And so we're going to construct the divisor graph of this element, but I'm only going to use the non-trivial divisors, even though technically the graph would consist of all divisors. And we see that the zero divisor graph of the Boolean ring on 8 elements arises from this X divisor graph. Note that these two vertices, for example, are adjacent because their product is equal to X. And it's easy to see in this case why we wind up with a zero divisor graph if we delete the first components. Because after deleting the first components, now we see that two vertices are adjacent precisely when their product leaves only zeros. And therefore, it follows that this will be a zero divisor graph of a Boolean ring. And so that's not really a proof, but it gives intuition for why this result holds. So we've seen that from the previous result that X divisor graphs in Boolean rings turn out to be zero divisor graphs. And now we'll address the question of what can be said about rings that are not Boolean. Of course, in a Boolean ring, every element is idempotent. And it turns out then that in any ring, even if the ring is not Boolean, if you choose an idempotent element X, then any component of the X divisor graph will be isomorphic to a zero divisor graph. That's provided that the component contains a square root of the element X. In the case where the component does not contain a square root, the component will be isomorphic to this tensor product.
Hello, Ivy.
Of the complete graph on two vertices with an unrestricted Bex graph. Unfortunately, it does not hold that this result will remain true if X is not idempotent. So here we have a ring that has an X divisor graph whose diameter is at least 4, but that never happens with zero divisor graphs or these tensor products. And so we see that this result cannot be extended to elements X that are not idempotent. However, if we replace the idempotent condition with the condition of R being von Neumann regular, well then the result does hold, even if X is not idempotent. And so in particular, as I mentioned toward the beginning of this talk, this shows that an X divisor graph will have at most 2 components up to isomorphism in the case where R is a von Neumann regular ring. If we combine both of those conditions, so if R is von Neumann regular and X is an idempotent element, then if we look at the compressed component, then it will be isomorphic not only to a zero divisor graph, but the zero divisor graph of a Boolean ring. Again, this is in the case where the component contains a square root of the element X. And it's interesting to note that this result generalizes the well-known theorem from Anderson, Levy, and Shapiro from 2002, where they proved that the compressed zero divisor graph is isomorphic to a Boolean ring anytime that R is von Neumann regular. And for the sake of completeness, I should point out that the compressed graph is found by identifying vertices that have the same adjacency relations. And so this corollary follows from the theorem by setting X equal to 0. Until now, we've been constructing graphs from rings, and now we're going to reverse that concept. So now, beginning with an arbitrary simple graph, we will build algebraic structure. To show how we will do that, we'll define the annihilator of a subset of vertices. So given a subset of vertices of any graph, not necessarily a zero divisor graph, its annihilator will be the collection of all vertices that are adjacent to every vertex in that set. So for example, the annihilator of this vertex A consists of the vertices B and C, since those are the vertices that are adjacent to A. In particular, we already see then that the annihilator of a single vertex is nothing more than the usual neighborhood of that vertex. Similarly, the annihilator of B consists of the vertices A and C. The annihilator of C consists of the vertices A, B, and D. And the annihilator of D only consists of the vertex C. But we also see that this annihilator is the annihilator of the set containing A and B. And so now we see that when the set contains more than one vertex, the annihilator is no longer the usual neighborhood of that set. And so in fact, this annihilator turns out to be the annihilator of several collections of vertices of this graph. To complete the set of annihilators of this graph, the annihilator of A and C consists of B. The annihilator of B and C consists of A. And then finally, by definition, we let the annihilator of the empty set be the collection of all vertices. And then for every other set that we haven't mentioned, for example, the set of all vertices of the graph, the annihilator will be the empty set. And so here we have the full set of annihilators for this graph. And it turns out that for any simple graph, the collection of annihilators will be a complemented lattice under inclusion. And here we've drawn out the Hasse diagram for the complemented lattice associated with this simple graph. And I'll point out that the complement of an annihilator is found by taking its annihilator. And that's where the notation C comes from, because applying C results in the applying C results in the complement of an annihilator. There are a couple of special cases involving zero divisor graphs that are worth mentioning. So first, if R is a Boolean ring, then under the partial order that we mentioned earlier, R becomes a Boolean algebra. And then it turns out that that Boolean algebra will be isomorphic to the lattice of annihilators that comes from the zero divisor graph. To illustrate that, let's return to the earlier example and let us add a couple of vertices so that we now have the zero divisor graph of the Boolean ring on 8 elements. So how does that affect the set of annihilators? Well, now the annihilators of A and B get a new vertex added to their sets. And then the annihilators of the new vertices were already accounted for by annihilators of other sets in the graph. And in particular, the lattice of annihilators is not affected by adding these two vertices. And so here we have the lattice of annihilators of the zero divisor graph of this Boolean ring. But it's easy to check that this complemented lattice is actually the Boolean algebra that arises from that Boolean ring, which illustrates our earlier theorem. The second special case generalizes the first special case. Note that for a commutative ring that does not have non-zero nilpotent elements, the collection of ring theoretic annihilators is well known to be a Boolean algebra under inclusion. But if we begin with a subset of vertices, then the ring theoretic annihilator is nothing more than the graph theoretic annihilator, except for the element 0. And that gives us a correspondence between ring theoretic annihilators and graph theoretic annihilators that actually turns out to be an isomorphism of partially ordered sets. And so in particular, for a commutative ring without non-zero nilpotent elements, the lattice of annihilators of its zero divisor graph turns out to be a Boolean algebra. So these special cases show that for zero divisor graphs of reduced rings, the lattice of annihilators of the zero divisor graph will be a Boolean algebra. And it's natural to ask which graphs produce Boolean algebras. This is the graph that we looked at earlier, and note that it's not a zero divisor graph of any ring, but its lattice of annihilators is a Boolean algebra. Although it's not a zero divisor graph of any ring, it is, however, a zero divisor graph of a partially ordered set. Notice, for example, 0 is the only lower bound of the vertices C and D, and therefore in the zero divisor graph, D is adjacent to C. And so it turns out that being the zero divisor graph of the partially ordered set is enough to conclude that the lattice of annihilators is a Boolean algebra. So in fact, for any simple connected graph with at least two vertices, the lattice of annihilators is a Boolean algebra if and only if the graph is isomorphic to the zero divisor graph of a partially ordered set. And note that this theorem recovers that second special case because we've already seen that for rings without non-zero nilpotent elements, the zero divisor graphs of the zero divisor graphs in the ring theoretic sense are isomorphic to the zero divisor graph in the partially ordered set theoretic sense. And so this theorem then tells us once more that the lattice of annihilators of the zero divisor graph of a ring without non-zero nilpotent elements is a Boolean algebra. And for the remainder of this talk, we will consider eigenvalues and adjacency matrices of zero divisor graphs. And we'll also see how zero divisor graphs of finite Boolean rings can be recovered from Pascal's triangle. So notice here, again, we have the zero divisor graph of the Boolean ring on 8 elements. And I've numbered the vertices. And here we have a matrix where, for example, since 3 is adjacent to 5, if we go to the 3rd row and the 5th column, we find a 1 to indicate that adjacency relation. And on the other hand, for example, in the 2nd row and the 3rd column, there is a 0, indicating that the vertices 2 and 3 are not adjacent. And so adjacency matrices contain all of the adjacency information in a graph. And it's worth noting that adjacency matrices are symmetric matrices. And so in particular, the complex eigenvalues are going to be real numbers. And also I should point out that the numbering, in terms of eigenvalues, the numbering of the vertices is irrelevant because any 2 orderings of the vertices will yield similar matrices and will therefore have the same eigenvalues. To see how the adjacency matrix can be recovered from Pascal's triangle, here I've listed the first 8 rows of Pascal's triangle because this is a Boolean ring on 8 elements. And more generally, for a Boolean ring on n elements, we would want to consider the first n rows of Pascal's triangle. We turn this into a matrix by letting all of the entries above the anti-diagonal be equal to 0. And if we were looking at the unrestricted Bex graph, which we will do shortly, then we would proceed with this matrix. However, since we're looking at the Anderson-Livingston graph, which excludes the 0 element and the 1 element, the identities rather, in the ring, we're going to omit the first and last rows and columns of this matrix. That leaves us with a matrix which I'll refer to as a truncated Pascal matrix. And reducing these entries modulo 2, all of the odd entries, which I've highlighted in red, will become 1. And all of the other entries become a 0. And there we have it. We've recovered the adjacency matrix of this zero divisor graph. And it turns out there's nothing special about this zero divisor graph. For any zero divisor graph of a Boolean ring, if you reduce the entries modulo 2 of the corresponding truncated Pascal matrix, then you will arrive at the adjacency matrix of that zero divisor graph. The upshot is that now results from elementary number theory become at our disposal to study zero divisor graphs. One particular theorem, which I won't state precisely, but is important for finding the eigenvalues, which I'm about to outline a proof for, is Lucas's theorem. It's a result that will help us reduce binomial coefficients modulo 2. And an application of that theorem can be used to show that if you cube the adjacency matrix corresponding to a Boolean ring and reduce the entries modulo 2, you'll always wind up with a matrix of 1s except down the main diagonal. So in other words, the cube of an adjacency matrix of a Boolean ring will always be the adjacency matrix of a complete graph after reducing the entries modulo 2. Well, then adding the identity matrix to the cube of the adjacency matrix, therefore results in a matrix, all of whose entries are equal to 1. Now, the effect of multiplying by a matrix of ones on the left is that it adds the columns of whatever the matrix is on the right. And so if we let the matrix on the right be the adjacency matrix added to the identity matrix, then we'll get the 0 matrix after reducing modulo 2. To see why that happens, well, it's well known that the degree of any vertex in the 0 divisor graph of a Boolean ring is odd. And therefore, by adding the identity matrix, now all the columns will have an even number of ones, so that multiplying by the matrix of ones will yield, after reducing modulo 2, a 0 matrix. Now, what this shows is that the adjacency matrix of a Boolean ring is a 0 of this polynomial given here over the algebraic closure of Z mod 2. And in fact, from that result, it becomes rather straightforward to determine that this is actually the minimal polynomial of the adjacency matrix over the algebraic closure of Z mod 2. And in particular, the eigenvalues of the adjacency matrix of a Boolean ring are precisely the eigenvalues of this polynomial, again, taken over the algebraic closure of Z mod 2. It's easy to check that the zeros of this polynomial are precisely the non-zero elements of the finite field of order 4, and that gives us a complete characterization of Boolean rings. So in fact, a finite ring will be a Boolean ring if and only if it's either Z mod 2 or the Boolean ring on 4 elements, or if its eigenvalues are precisely the non-zero elements of the finite field of order 4 taken over the algebraic closure of Z mod 2. So to close this talk, we'll consider eigenvalues over the real numbers. We've just seen that we can determine all of the eigenvalues over the algebraic closure of Z mod 2. But what about the eigenvalues as real numbers? And this question remains open, but we do have several results that get us pretty close to answering this question. First, note that a ring, a finite ring rather, is a Boolean ring if and only if it has the property that lambda is an eigenvalue of its adjacency matrix, if and only if either its reciprocal or the negative of its reciprocal will also be an eigenvalue of the adjacency matrix. And then, as far as the numerical values of these eigenvalues, it turns out that the eigenvalues of a Boolean ring are precisely the eigenvalues of these two Pascal type matrices. So for example, here we have the Boolean ring of order 32. And so rather than determining the eigenvalues of the resulting 30 by 30 matrix, we find that the eigenvalues are precisely the eigenvalues of these two 4 by 4 Pascal type matrices. And the good news also is that the eigenvalues of these matrices are already well known from Karlitz in 1965. And therefore, the problem of determining the numerical values of the eigenvalues of a Boolean ring reduces to the problem of just determining the eigenvalues of this matrix, which, as far as I know, remain unknown. And so finally, while we are still unable to determine precisely all the numerical values of the Anderson-Livingston graph of finite Boolean rings, it turns out we do know all of the numerical values of eigenvalues for the unrestricted Bex graph for Boolean rings. And so in fact, it turns out that the eigenvalues for the Boolean ring of order 2 to the n will consist of all of the monomials of degree n taken in the golden ratio and its conjugate over the rational numbers. So in other words, we're looking at monomials of degree n in zeros of this polynomial. In fact, we can do even better. And so for the final result of this talk, we characterize all of the eigenvalues for not just a finite Boolean ring, but for any finite ring that has no non-zero nilpotent elements. So to explain this result, recall that a finite ring that does not have any non-zero nilpotent elements is guaranteed to be a finite direct product of finite fields. And so it turns out then that the eigenvalues are going to be all possible products of the zeros of these polynomials, with one factor taken from each possible polynomial. Note that in the case of a Boolean ring, all of these values of Q are equal to 2, and therefore this polynomial is just the polynomial from the earlier result, showing that this theorem generalizes the theorem for Boolean rings. And that is the last result for this talk. And so I suppose now I can take whatever questions you might have. If any. It's been a long day for you, but the day is just starting for me.
Okay. Mukti ma'am.
Any questions and queries from the participants or people present in the conference?
John, just I have a doubt, may not be the question. Is there any recurrence relation on the eigenvalues of this Pascal triangle? Because the original problem is reduced to problem of finding the eigenvalues for the Pascal triangle. In fact, in your case, it is 4 by 4. Is there any recurrence relation? Anything further to reduce the problem? Or?
Well, so I believe you're referring to this result, that the eigenvalues are precisely the eigenvalues of these two Pascal type matrices.
Yeah.
Okay. Carlitz found the eigenvalues for these matrices, which you'll notice are the negatives of, this is a full Pascal type matrix. You've got the full Pascal matrix here, whereas this one is truncated. Okay. And I am not aware of any other results for these Pascal type matrices.
I have a question.
Yes, sir.
Yeah, actually, you have proved there is a result says that X divisor graph is isomorphic to zero divisor graph of a Boolean ring, right? In that time, that X is any arbitrary X, right?
That's correct. And you were talking about the X divisor graphs?
Is isomorphic to the zero divisor graph of a Boolean ring, right?
That's correct. Yes.
Yeah, that means that X is an arbitrary X, right?
That is an arbitrary X, yes.
Yes. Similarly, I have seen some of the results concerning about the compressed zero divisor graph of X of the Boolean ring is, so it seems like that X may not play any role on the Boolean ring, right? Either it is a X divisor graph or it may be a compressed zero divisor graph. A particular value of the X or a particular element X may not play a role, right, in terms of Boolean rings.
Right. So it need not be an L. Let me find the result that we're talking about.
One case, it corresponds to annihilator of X. at least in one case.
So is this the result that you're referring
Yeah,
to?
here this.
No, the previous result, the one you may go back,
Okay.
previous. Yeah, this one.
Yes. Okay. Yes. So X, this can be any element of a Boolean ring. And so here, this is the X divisor graph, but it's isomorphic to the zero divisor graph.
Yeah, which means this X has not play any role, right? The elements of the Boolean ring may not play any role, right? In terms of graphs.
So the elements of the Boolean ring may not be. I'm sorry. How did you refer to them?
Since I'm just listening that X may be any X, right? Any element of the Boolean ring.
No.
That's correct.
This graph.
So one side is it depends upon some X, an element. The other side is isomorphic to zero divisor graph. It is common for entire ring, right? So this is what my question. So what I feel is in terms of Boolean ring, the element may not play a vital role.
May not be what?
Yeah.
Well, what he claims is whatever be the X you are taking, you will get the same zero divisor graph. Asir, am I correct?
Yes, exactly. That what.
Okay.
But
So
I don't think so, because for this X only, this is the graph. John, suppose if you take some other X, what will be the graph?
yeah. So when it depends on the element. If you increase the number of non-zero components, then you will get a zero divisor graph of a Boolean ring of smaller order.
Yes.
Okay. So the ring varies, right? Whenever you change the X, correspondingly the ring is also changes, right?
Yeah, definitely.
That's correct.
It's not the same. It is for a suitable ring, or maybe I can put it that way.
Okay. So what I thought is initially that for every X in the ring, the Boolean ring is unique, but it's not the case. Yeah.
That is not the case. Yes.
There is
That's a good question.
There is R such that this property is being.
Okay.
May I ask?
Joshi, please.
Yeah. Just regarding this question again, can we, because you proved one algorithm regarding the how to draw the zero divisor graphs of direct product of integral domains, right?
For integral domains?
Yeah, direct product of integral domains. So can we go a little ahead and instead of Boolean rings, you are looking at divisor graphs. Can we go a little ahead? And is there any relation if you choose particular X, which type of zero divisor graph you are getting? So since you are saying that you are getting a zero divisor graph of a smaller Boolean ring. So is there any relation between the order of that smaller Boolean ring and the original one? This is one question. And second question is regarding the eigenvalues of Boolean algebra. Can we extend it to Boolean posets as such, partially ordered sets? Because from finite Boolean algebra, if you remove W reducible elements, that means which is a union or a meet of any two, reducible, not irreducible, reducible, then whatever under induced partial order, whatever you are getting, that is a Boolean poset. So do you have any idea how the eigenvalues will play? Because what we observed in Boolean posets, the eigenvalues are not reciprocals as such.
So for more general Boolean posets, I do not know the extent to which our result from this talk applies. Now for Boolean posets in general, they do not necessarily yield complemented graphs. Is that true?
They are the complemented graphs.
They are complemented?
Yes.
Okay. Yeah, well, I'm not sure. I'm not sure whether the result will extend or not.
Okay.
So now regarding your first question, was it with respect to this result?
Yeah. No, previous.
Oh, previous.
Sir, Asir asked about it. The same question.
Oh, the same one. Okay. And
Yeah.
so this one here.
Yeah. So it is Z2 cross Z2 4 times. It is Z2 cross Z2 3 times. So when you are removing, does it play with zeros, number of zeros in the tuple X you are looking at? Is there any?
Good guess.
That is what it is. Yes. That's, so for example, here, the element X had 3 zeros.
Yeah. Okay.
Yeah, good guess. Maybe.
Now, but please keep in mind that, you know, that gives intuition, but for a more general proof, not every Boolean ring is a direct product. So this observation is really just for finite Boolean rings, or more generally, Boolean rings that are direct product. But nevertheless, this gives us intuition for the more general result. Yeah, good question.
Good.
Yeah. I have one more question as well.
Please.
Hello.
So yeah, I have one more question. So you have construct annihilating ideal, right? Something like from graphs to algebra. You have chosen a set, something like a neighborhood set, right?
Yeah.
So I'm sorry, could you repeat? I was unable to hear.
Taking a graph and you are taking neighborhoods and constructing the ring or Boolean algebra.
Exactly.
Later. Next. Yeah, here.
Yeah, this one. So you have mentioned this as annihilator of A. So my question is whether this CA is a form and annihilator of the corresponding ring, Boolean ring.
Exactly. In terms of graph theoretical notation, they are neighborhoods.
These are neighborhoods, yes. So this,
yes.
Once you have constructed the ring, are these elements happen to be the annihilators of the corresponding element?
They are.
Or they happen to be like that?
Yes. So let me go back to the correspondence. Let's see. So, there it went. This correspondence here.
Yeah.
Yes,
okay.
Exactly.
Yeah, so beginning with so if we have a zero divisor graph, then any subset of vertices, the annihilator is in the ring theoretic sense, the same as the annihilator in the graph theoretic sense, except for zero. This is as long as the ring does not have any non-zero nilpotent elements, or this result is no longer valid.
Fine. Exactly.
Yeah, very interesting result. We have very strong connection between the graphs and the corresponding annihilators, right?
Correct. Yes.
Especially instead of studying the annihilators in the Boolean ring, we can consider then just a neighborhood of a corresponding graph, right?
That's correct. Yes.
Thank you.
And that's true not just for Boolean rings, but for any commutative ring.
Yeah.
As long as it has no non-zero nil.
The degree of the Anderson-Livingston graph, the degree is nothing but cardinality of annihilator of A minus 0, comma A.
Yes.
Actually, we realized it. Okay.
Yes, these are the properties that, but here is they exactly consider connecting the annihilating ideal itself.
The other way is also true.
Yeah, it is very strong because even the annihilator set is directly constructed from the graphs.
Yes.
So,
hello.
This result, do you have studied this result for any other graphs except zero divisor graphs?
Yes. So, so for arbitrary graphs, there are several papers that where this is used to determine whether a graph is realizable as a zero divisor graph. So there are several results. For example, characterizing when a graph is a zero divisor graph of a reduced semigroup, for example. And again, these results are all starting at the outset with an arbitrary graph, not necessarily zero divisor graph. And so, for example, as noted in, see if we can find the previous slide here, for a graph G, even if it's not a zero divisor graph, we're going to have a complemented lattice in any case. And so already we're coming up with algebraic structure from arbitrary graphs, not necessarily zero divisor graphs.
Yeah, thank you so much. Thank you.
Thank you.
Hello.
Mukti ma'am, please.
I have one question.
There is
Yes,
one boy, a participant raised the hand, Gahini na Anavane.
Yes, sir.
Yes, sir.
Hello.
Yeah, please proceed.
Sir, you have constructed Pascal type of matrices Pk and Qk. So what was the motivation or intuition of that construction? This is my one question. And second, can we extend similar constructions for other graphs? For example, ZP power n or other zero divisor graphs?
Okay, and which construction were you asking about?
Pascal type matrices Pk and Qk, whose eigenvalues collectively gives eigenvalues of Boolean ring, zero divisor graph of Boolean ring. Yes.
Okay, so for the eigenvalues, and so which construction? Let's see.
Specifically of Pk, first matrix.
Okay, so is this question
Yes,
about this one? Okay, so for about the Pascal matrices?
Yes, sir.
Okay. And your question is about whether more generally reducing Pascal matrices modulo 2, what they say about graphs besides zero divisor graphs of Boolean rings?
You have proved that eigenvalues of this matrix are nothing but eigenvalues of zero divisor graph of Boolean ring. So how this matrix is constructed? So what is the motivation?
Oh, the motivation, in terms of applications, is this theorem here, Lucas's theorem, becomes applicable. So this is a theorem that helps us reduce binomial coefficients. And Pascal's triangle is really, the elements of Pascal's triangle are binomial coefficients. And so if we are able to recover adjacency matrices from Pascal's triangle, then these results from number theory can then be used to learn about the adjacency matrices. Now that's one, but also it addresses the problem of when a graph is realizable as a zero divisor graph of a Boolean ring. And so if I give an arbitrary graph, how can we tell if it's a zero divisor graph of a Boolean ring? Well, in general, that can be difficult, but zero divisor graphs of Boolean rings are recovered from Pascal's triangle. And so that is the second motivation. Have I addressed your question?
Can we construct similar matrices, Pascal type of matrices for other graphs like ZP power n?
I am not aware of such constructions. Perhaps there exist constructions for that, but I'm not aware of them. However, do keep in mind that for the unrestricted Beck graph, which I'm moving to here, for the unrestricted Beck graph, we're able to come up with the eigenvalues for any finite reduced ring, not necessarily Boolean, but any ring. But as far as determining the adjacency matrices from some sort of construction from Pascal's triangle, I am not aware. Perhaps yes, perhaps no. I don't know. It's a good question.
Thank you, sir.
Ma'am, please
Thank you.
conclude. Ma'am, please.
Can I conclude now?
Yeah, please. So,
Yeah, I'm very much thankful to Professor Lagrange for delivering endowment lecture, Professor Sambat Kumar, for his thought-provoking lectures and igniting the minds of the researchers with respect to the topics he has spoken. And with this one, I extend my warm regards to him. And as far as I am concerned, I thank ADMA members, ADMA committee who has taken care of this one, as well as the MSU University and their faculty, giving me an opportunity to chair the session. Thank you very much.
Thank you.
Ranjini,
so
please. John, thank you very much for your nice talk, and it is really wonderful. And I will be in touch with you.
Thank you so much. And it's so nice
Thank
to
you.
meet all of you.
Yeah,
And
yeah.
Thank you for the opportunity. I look forward to
Thank you.
speaking with you in the future.
Fine. Thank you. Ranjini, please conclude.
Thank you, sir. Thank you for such an informative session.
Please.
I also extend my gratitude to Professor Dr. Mukti Acharya, who initiated the session by introducing the speaker to us. Thank you, ma'am.
Thank you.
Please announce that ADMA GB starts immediately.
Yes, sir. The ADMA general body meeting starts now. Thank
And
you.
we hand over the proceedings to the ADMA officials.
Yes.
You make Professor Muthusamy?
Yes, sir. And
Please. And our people will assist for anything.
I
And
just see
there
that.
are, yeah.
Professor Seduraman, sir.
Good evening, sir. Good evening.
Good evening.
Good evening, sir. Good evening, sir.
Shall we start this meeting?
So we have to wait for some more people to join, right?
Yeah, whether